Hi, good morning students. Today we are discussing about nodal analysis with AC excitation. That is, if an AC network is given, how to apply nodal analysis to that given network to find any response. So as we know that nodal analysis is derived from Kirchhoff's current law. Kirchhoff's current law is nothing but algebraic sum of all the currents at any particular node equal to 0. So we can apply this nodal analysis just by identifying the number of nodes in the given network. Out of all these network, any one of the node is taken as reference node. Except that reference node, we are going to apply KCL at each and every node and writing its KCl equation. Later on, after solving these KCl equations, we will get unknown node voltages. So that's why this method is also called node voltage method or nodal analysis. So nodal analysis for DC network is familiar, then anybody can be able to apply this nodal method to an AC network also. Simply a DC network which contains only resistors and an AC network which deals with impedances. So now let us see how to apply this nodal analysis to any given AC network. Here I am going to consider a problem. Determine V0 of t in the given network using nodal analysis. Here V0 of t is nothing but voltage across this element. Here this is an AC network. This AC network contains all type of elements like resistors, capacitors and inductors, and it is AC current source, and here this is the voltage across inductive elements. This voltage we need to find using node voltage method. Here the first step is, for the given network we need to identify how many number of nodes are there in the given network, and we have to assume those unknown node voltages, and out of all the nodes we have to take any one of the node as reference node. So except that reference node, we are going to apply KCL and then writing the KCL equations. So for that, now let us see, this is our given network. Here for this network, it contains 3 nodes, node 1, node 2, node 3, and out of these, this is the common node. So that's why I have taken this node as reference node. Otherwise we can take any one of the node. Here I am assuming that V1, V2 are the unknown node voltages. These are the unknown node voltages we are going to find using this node voltage analysis. So here for these unknown node voltages, we are going to apply KCL, Kirchhoff's current law, at all these nodes. Here I am going to, in the next step, I am going to apply KCL at node 1. So here this is our node 1. I need to apply KCL at this node 1. So for that, what I am doing here, in order to apply KCL at any node, I am going to consider the elements which are connected to that node only. If I take the network in which only these 3 elements are connected to node 1. So just what I am doing is just represent all the nodes, V1, node 1, node 2 and reference node. Just I am representing the elements which are connected to this node. Current source, 30 ohms resistor, 10 ohms resistor. Here, before applying KCL, just I am going to treat the node at which I am going to apply KCL. Here this is the node at which I am going to apply KCL, taken as positive with respective to all the remaining nodes. So hence these two are taken as negative. So here we are assuming that this node is at higher potential compared to the remaining nodes. So that's why I am taking this node as positive with respective to the other. So here this is a current source. Its direction is given. It is flowing towards the node. And here this is at higher potential and this is lower potential. Current is flowing in this direction, I am assuming. Here also higher to lower. So that's why I have taken current directions here like this. So I am going to apply KCL at this node such that algebraic sum of all the currents, means sum of currents entering towards the node is equal to sum of currents leaving the node. Here it is having only one entering current and 2 outgoing currents. So that's why I am taking one entering current, it is given as minus 5J, and 2 outgoing currents as outgoing current. Now I need to find current flowing through this element, that is I is equal to V by R. Here V is the voltage across these 2 points, that node and ground. So V1 is the voltage across 30 ohms and R value is 30. So that's why I have taken V1 by 30. Similarly 10 ohms is the resistor connected between V1 and V2. That's why this is the voltage across 10 ohms branch as V1 minus V2. So since it is at higher potential, so I am writing voltage across 10 ohms branch is V1 minus V2 and its impedance or resistance value is 10. So here this is the KCL equation I got. Then for simplicity, I am going to multiply the whole equation by 30. So I'll get, if it is multiplied by 30, 30 cancelled out, I have V1. And here it is also 30 by 10. So 3 times of V1. And here it is minus 3 times of V2. It is equal to minus 5 into 30 as minus 150J. So on simplifying, I got the equation 4V1 minus 3V2 is equal to minus 150J. Similarly, I am going to apply KCL at node 2. So here coming to this network, at node 2 I am going to apply KCL. Just I am going to consider the elements which are connected to node 2. So how many elements connected here? 1, 2 and this is series combination. 3 elements connected. So just I am going to draw those 3 elements. 1, 2 and this is series combination of elements. Similarly, if I want to find out apply KCL at node 2, so it is treated as positive and the remaining all are negative. So higher potential to lower current, direction of current. So current is flowing like this and here also like this and here also like this. So if sources are given, that source direction will be given in the network. So we no need to represent the current direction for this. But here no sources are there. So all element for which we need to represent the current directions. So here current flowing, all are outgoing currents. So algebraic sum of all the currents will be equal to 0. Then outgoing current plus outgoing current plus outgoing current. So this is the current flowing through 10 ohms branch. Its voltage is V2, higher potential minus lower potential. V2 minus V1 by 10 and here it is V2 minus 0. So simply it is V2 by its capacitive reactance value is minus J20 plus here because I is equal to V by XC. Here XC, V value is V2 by XC value is minus J20. So like that we need to write current flowing through each and every branch. Similarly here also voltage across this branch is V2 and the impedance value is 10 plus J10 R plus JXL. So like this I am going to write the KCL equation which are all outgoing currents. So sum of all the outgoing currents will be equal to 0. Then for simplicity I am going to multiply this equation throughout by 10. Then I have the current equation, the KCL equation like this. After multiplying the total equation by 10, I have V2 minus V1 plus V2 by minus J2, V2 by 1 plus 1J. So for simplification, I am rewriting this like this as minus V1 and this is V2 and V2 by minus J2. I am going to multiply this term J with J. So we have J multiplied by J, it will be minus 1. So if I multiply this by J, and J square is minus 1, minus of minus plus. So finally I have J by 2 V2, J by 2 V2 and here I am going to rationalize the term. It is A plus JB. So I need to multiply it by A minus JB. So A plus JB and A minus JB will be 1 plus J into 1 minus J is equal to A square plus G square, B square. On simplification, I have the equation like this, V1 plus V2 plus V2 by 2. Here JV2 and minus JV2 cancelled out. So I have the equation like this. So finally V1 is equal to 3 by 2 times of V2. This is the relation I got here. Then after substituting third equation, in first equation, so I have what is our first KCL equation? 4V1 minus 3V2 is equal to minus 150. So this is our first equation. In this I am going to substitute third equation. So 4V1 minus 3V2 minus 150. 4 multiplied by, instead of V1 I have 3 by 2 V2, just I am going to substitute here. After simplification I got V2 is equal to 50J. 50J is nothing but in polar form it is 50 at an angle minus 90. Similarly I am going to find V1 also. V1 I have the relation 3 by 2 times of V2. So here this is from this expression. Then I can find V1 as 75 at an angle minus 90. Here I have V1 and V2 which are the unknown node voltages which we have assumed. But in order to find out V0, we have to apply voltage divider rule. Why? Because here R, XL, these two are in series and the total voltage across this element is V2. So if V2 is the total applied voltage which is divided across resistor and inductive reactance. So for that I am going to apply voltage divider rule to find out V0. V0 is the voltage across inductive reactance value. So for this I am going to apply voltage division rule. Here V2 is the total applied voltage, V0 is the voltage across inductive reactance. So V0 will be equal to total applied voltage V2 into the same branch impedance by the total impedance. Same branch impedance is J10 and the total impedance is R plus JXL, 10 plus J10. So on simplification we have minus 50J, 10J by 10 plus 10J. Then on simplification we have, after rationalizing 50 by 1 plus J, after rationalizing this term we have V0 is equal to 25 minus J25. This is our final answer, 25 minus J25. So similarly, we can apply this nodal analysis to any kind of given network simply just by applying KCL at each and every node to get that Kcl equation. So after manipulating those Kcl equations, we can simply find out our response which we want to find. So similarly, we can solve. This is also an AC network in which we can apply both mesh current and node voltage analysis. Simply mesh current analysis, we need to identify the loops. After writing the loop equations, we can find out the response. Here we need to find out V0 of t. And in node voltage method, here these are the nodes where we have to apply KVL. But here we don't want to apply unknown node voltage. Why? Because here the node voltage is given 10 at an angle 0. And this is also one more network, AC network. Here we need to find out V1 and V2. V1, V2 are the unknown node voltages which we want to find out using node voltage method. So simply we can apply KCLs at these two unknown node voltages. Node voltages which we can determine easily. Thank you.